Good morning, everyone. Thanks for attending this seminar of our thematic project. My name is Carlos de Marqui from EESC-USP. I'm one of the PIs of this project, together with my colleagues Leopoldo de Oliveira from EESC-USP too, Domingos Alves Hadi from ITA, José Roberto de França Arruda and José Maria Campos dos Santos from Unicamp. And Mike Brennan and Paulo José Palpites from Unesp, Ilha Solteira and Bauru, respectively. As you know, our project is organized in 4 work packages: nearly periodic structures and coupled metamaterials, metamaterial structures, metamaterial design and optimization, nonlinear periodic structures, and smart metamaterials. And what we expect from the intersections of these work packages is that we can promote new insights and applications with potential for scientific and technological innovation. In this sense, I do believe that cooperation and collaboration are key points or key words in our project. So although we have 4 packages, we have we have researchers being developed in between these packages. So the intersections are really important for us. This is our tentative schedule today. This opening later, Professor Leopoldo de Oliveira will show his recent results on smart metamaterials, in particular membrane metamaterials. After Leopoldo, Danilo Beli will talk about wave beaming and diffraction in quasicrystals. After Danilo, Jaime A. Mosquera Sánchez will show his recent results on nonlinear periodic metamaterials. Danilo and Jaime are postdocs in my group. Then Renan L will talk about space-time wave localization in piezoelectric metamaterials. After Renan, Camila Schmidt will talk about piezoelectric energy harvesting from disordered metastructures. Renan and Camila are master students. After all the presentations, we will open for discussions, for comments and questions, and then we expect to finish about 11:40. I remember that all these meetings have been recorded and are available in our website. Most of our, at least most of the results from my group, from Danilo, Jaime, Renan, and Camila, are numerical results. So before I invite Leopoldo to start his talk, I would like to show some experimental setups that are available in our lab. And my motivation is, if you believe that one of these setups could be useful for you, for your research, just talk to us, just send an email or contact us that we can help. We can share these setups if you think they are useful. We have some previous experience with Wagner Souza, that nowadays is an assistant professor at Unesp São João da Boa Vista, with shape memory alloys-based metamaterials. So we have this experimental setup with a beam and SMA-based resonators. It's a thermomechanical system where we can control the band gap position by controlling the temperature of these resonators. We also have some experience with piezoelectric metamaterials combined with analog shunt circuits. And more recently, we developed some digitally controlled analog circuits that we could obtain this super wide attenuation zone in a piezoelectric metamaterial. It's reported in this paper. More recently, we started to develop some digital shunt circuits in order to replace the analog shunt circuits. And the idea is to improve this tunability or this adaptability of these metamaterials. And these digital shunts have already, they are working, and we could validate against for a resistive shunt and for a resistive inductive shunt. So these are numerical, the analog and the experimental results for the digital shunts, so they are working. What's interesting in this case, if you compare this picture here, so this is the experimental setup for a single unit cell. It's a beam with piezo. If you compare with this previous one, where we were using these analog circuits, the quantity of electrical elements and connections here have been reduced to only a few elements here, since everything is inside the digital board. This digital shunt will be used in this, sorry, the picture is not very good, in this metamaterial beam. It's an aluminum beam with 12 piezos periodically distributed along this beam and connected to this digital shunt. So if you believe that one of these setups or this previous experience can be useful for your research, please just contact us. We are available to collaborate or to help if you think it's useful. Okay. So again, to our schedule, I'd like to invite Professor Leopoldo de Oliveira to share his screen and start his talk on membrane smart metamaterials.
So, good morning, everyone. My talk today will be regarding work package number 4, where I stand as coordinator of this work package. I will focus mainly on the results. I'll try to stick with time because I want to cover 3 studies that we've been doing recently. So just as a general picture of what we figure for work package 4, we consider unit cell designs that incorporate smart materials. And in a broad sense of smart materials, including piezoelectric elements, shape memory alloys, as Carlos has shown, but also if we have magnets, for example, included in the structure, also to augment the dynamic behavior or promote some special nonlinearity or dynamic behavior, would also be considered under the framework of this work package. Of course, for metamaterials, we consider that these unit cells will be repeated along a host structure, and this host structure can be of many kinds, including here, for example, things that we consider here in São Carlos, which is aeroelastic systems or vibroacoustic systems, or even structures that could be dedicated for aerospace applications. So the first example I want to show you was like a clumped beam, where we include an increasing number of those unit cells to analyze the evolution of an attenuation band, because this is like a finite structure with boundary conditions, and the wave reflections here will promote such an attenuation band, not a band gap in the sense of a pure, ideally periodic structure. And as you see here, we were targeting the second resonant mode of the beam. And as from 10, 11, 12 elements, we reached a plateau on the performance. That there we decided to build a setup to experimentally verify this phenomenon. We start with a single degree of freedom mechanical resonance system and added piezoelectric elements and a shunt circuit with an inductor and internal resistance to realize this shunted unit cell. These are some simulations of the concept unit cell. This is built on plastic material, so on 3D printing. The piezo disc is glued to the beam, and this thinner part here will be the flexible element of our single degree of freedom system. This is the concentrated tip mass. This is a picture of the first prototype with the disc. And since we are dealing with low frequencies, we need some synthetic inductor circuit here to represent the inductance at the level we need. We did some validation of the unit cell first, and then we go for the full assembly. Sorry if I'm going quickly here, but we added then this pair here, considering one unit cell, and then we started adding lateral ones until we reach 11 unit cells, or if you like, 22 of those elements glued to this aluminum beam. Shaker here gives us an input force, and then you have an output accelerometer here measuring the response. That's the transfer function we want to measure. Although we also measure vibrations at the tip of each element here, as well as monitoring the voltage across each piezoelectric element during the measurements. Here's a combination of frequency response functions we measured here. So this accelerometer by the force, and even in the driving point FRF here, we can already see an attenuation band forming as we increase the number of unit cells. I have examples of each of those experiments, but I'm going to jump straight to the full assembly. So, of course, when we have the empty beam, we have vibration modes as expected, first, second, and third vibration modes. When we put several of those resonators to the beam, we see, for example, in the first resonance that they will move in phase with the beam, as they were designed to resonate close to the second mode. When we go close to the second mode, then the attenuation starts to work, and as you can see here, the beam is almost standing still, as whereas the resonators, they vibrate resembling that second vibration mode of the beam. Not all of them do in the same way, because it's, again, an experiment. There is variability, uncertainty in the manufacturing process, as well as in the assembly, where we glue them to the beam. The effective length of the bending is a result of where we exactly glue it. So although we have jigs to try and make it as close as possible to each other, there is always some imperfection. And since it's a finite structure and we do have those reflections, we can assume that there will be some poles, so resonances, if you like, within the attenuation band. And these are some of the modes that we see there. You see again, there's various configurations of the elements vibrating, and the structure remains still. So I'm going to jump here. If you follow the arrow there, you can see where we are. So when we reach a peak that is close to the border of the attenuation band, then the structure starts to vibrate again. So what happens when we assemble everything there? So we now have these extra degrees of freedom you see in the border are the voltage across the piezos. And now we are just monitoring the voltage, as the shunted circuits are not connected yet, so it's an open circuit. And there, in the attenuation band, we see now the masses vibrating, and we can see some voltage going through the piezos. And okay, that's what we get from just a purely mechanical system, let's say, that is modified by the piezo, but without any attached circuits yet. Finally, when we do connect the shunt damping, the result looks like this. So the structure is standing still. Now you see the masses also vibrate, but not as strong as before. And we see a lot of the energy going through the electrical domain. And the vibration you see here also actually represents the voltage going through the shunted circuit, which is now resonating and taking that energy away from the system. As a second example, I want to talk about the membrane applications. We went for membranes because they will be very lightweight structures. And if we add a mass to the center of a structured membrane, we get what they call a decorated membrane resonator, which will exhibit these two resonance modes. Of course, in resonance, these systems will radiate a lot of noise, but in between those resonances, we expect to see an anti-resonance, and this anti-resonance is supposed to provide some transmission loss if we build a structure based on those decorated membranes. So we made some finite element model of the decorated membranes, and here are some values that have been updated based on these experiments that we carried out with the actual membranes. So this is like a latex rubber material that we stretch. We have a means to control the amount of stretching we provide. Then we build these frames that will give the final shape of the membrane. Here's an example with various shapes and sizes of membranes. We glue it to the stretched rubber and finally get a membrane that we can assemble in such a transmission loss setup and analyze its performance. For a single unit cell like this, here's a comparison of numerical and experiments, which come quite close. With that validated unit cell model, we then try to calculate what a periodic assembly of those membranes would provide in terms of sound transmission loss. And as we go up in this plot here, we see sound transmission loss increasing quite a lot. We also have some effects here due to the presence of the frame. The frame is also blocking part of the waves. And so the amount of transmission loss that we see here is a combination of the effect of the decorated membrane plus the frame. Okay, so, but if we are working with smart metamaterials, then we also want to incorporate some smart elements into the membrane design, and we did that by adding these piezoelectric discs here. So now we have different modes, of course, and when the system resonates, we have dips in the sound transmission loss. We want to target those, again, using shunt damping. So we add a circuit with shunt and with damping, inductance, resistances, and we attach it to the piezos, and this is what we get. So we indeed increase the transmission loss close to the resonance of the circuit. And this is simulation, again, based on this concept where we would have several of those smart membranes with their circuits attached. And when we increase the number of unit cells, again, we see a band gap that is forming close to the design frequency opening up. And we have some impressive results here for this numerical exercise that we still need to validate experimentally. Also, to give you a further view on what we want to address, we want to design those elements, those membranes, we want to assemble them in a way they will provide also an aesthetic solution, because if you want to have such solutions in concert halls or in rooms, it's often that they have to address also an aesthetic from the aesthetic point of view, but also because when you look to these different panels here, we have different sizes, and these different sizes could provide an interesting design for a super unit cell with various resonance frequencies, and then with that we could broaden the behavior of such lightweight solutions. To design such elements, for example, we can look into Islamic art. This is an example of how you derive those geometric shapes. And then interesting thing about these geometric shapes is from some lines and curves, you can draw some patterns that actually tessellate the plane. And by tessellation, I mean, when we look into geometry, you have those shapes that when they are combined, they will completely fool the space. So if you think about a panel, we have a 2D space, and when you derive any forms based on those figures, you have automatically something that fills the plane and could have interesting vibroacoustic performance. To address this, we already did some initial trials with these kinds of combinations. Of course, they are not squared repetitions of each other, so we still have to look into how to apply Fouquier block boundary conditions to analyze those in an infinite sense. But we could already build some of those, simulate in a unit cell level, and see that they indeed have several resonances that broaden a bit the effect of transmission loss close to those resonances and anti-resonances. We can add masses to some of those squares and not to others, and have indeed unit cells with several resonance frequencies. Just as a means of looking into the future a little bit, we want to further explore those smart elements inclusions and also have more complex circuits attached to them, so like nonlinear circuits, nonlinear energy sinks, and also explore aperiodicity. So still looking into this combination of engineering and art, we could look into Escher figures like that and think of panels that would change properties according to one dimension, and explore those also interesting aspects on metamaterials. I hope I did not exceed my time and did not speak too fast, and I'll be happy to answer questions in the end of the presentation. Thanks.
Thanks, Leopoldo. So, as I said before, we are going to open for comments and questions after all presentations. So back to our schedule. I'd like to invite Danilo Beli to share his screen and start his presentation on wave beaming and diffraction of quasicrystals. When you are ready, Danilo.
Hi everyone, good morning. Can you hear me? Because sometimes my microphone is not good enough, so the people cannot hear me. It's good?
It's good, it's okay.
Okay. Can you see my screen? Yeah?
Not yet.
Not yet. Yeah, it's coming.
Yeah, it's okay.
Okay. Can you see, the presentation?
Yes.
Yes, okay. So I will present this work that was developed in collaboration with Matteo Sosa and Massimo Lusini from University of Colorado Boulder. And I will start to explain a little bit about the quasicrystals and how to obtain these metamaterial plates first, and after I will show some wave phenomena and that is related to beaming and diffraction, okay? So let's start to define a crystal. Oops, maybe it's not working. Okay, now it's working. A crystal is defined as a periodic arrangement of atoms with a translational periodicity. So usually we have 3D or 2D or 1D systems. In 2D systems, let's take this case here of the hexagonal pattern. We have a unit cell definition, and if you translate this unit cell in space in X or Y, you can fill the space, the real space. And also we can compute the Fourier transform of this real space that is just by computing the Fourier transform of the material distribution. And you have this diffraction pattern that shows some crystallographic point symmetries that also follows the hexagonal pattern. So if you have some kind of symmetry in physical space, you also get these symmetries on reciprocal space. So for the periodic cases. So, and you have been using these crystals design to investigate phononic crystals and metamaterials in the last years. And we can do differently. We can use other kind of symmetries to provide a better way to manipulate waves, or in symmetries that is not allowed in the crystals. Let's see if this is possible. And in the 80s, Daniel Schattman discover the quasicrystals, a way to fill the real space without repeating the unit cells. And these quasicrystals also have this diffraction pattern that follows some order, but not in the order of the crystals that follows the 2, 3, 4, or 6-fold symmetry, in an order that has like a rotational symmetry, but not that is not allowed for the crystals, like this one that you have 10 peaks here with rotational symmetry. So it's possible to fill the space, but not with unit cells in a different manner that can have other wave properties too. So the people start to look on the quasicrystals, and they discover some phenomena related to superconductivity, and also topological states like Mateus presented last time, but also in mechanics to have like isotropic stiffness or failure resistance, or even in wave propagation to have different band gaps or even isotropic wave propagation. But here you are interested in the wave directionality and diffraction in high order fold symmetries that it was not allowed for the crystals. But first I will show you how to design these quasi-periodic plates. And after I will show you how to obtain some dispersion properties for these quasi-crystals and so on. Okay, so for the periodic cases, we have these rotational symmetries, and they are attached to this restriction theorem that it's possible to fill this space with these rotational symmetries in a tessellation procedure, where you can use 4-fold or 6-fold unit cells, or triangles, square unit cells, or hexagonals, but not pentagons. If we use pentagons to fill the 2D space, you have some gaps or voids, so it's complicated to fill the space with symmetries that is not this one that the crystals have. So how we can do that in a simple way? So we use a procedure that was presented by Lubensky, where we assign peaks in a circle in the reciprocal space. So the number of peaks here gives us the symmetry in the physical space. So we have peaks that are equally spaced in the reciprocal space. And by using this equation here, like inverse Fourier transform, you can recover the physical space. Like here, I assign just 2 peaks, so I have a bilayer distribution. And this bilayer distribution, you have the same spectral contents of our design, but here you have a peak in the middle that gives us the DC level, okay? Here we have also a threshold that I will not explain here, but in the next slide it will be more clear how this threshold works, okay? We can do the same for 4-fold symmetry that gives us like a square lattice. So here we have this unit cell repetition for the 4-fold, and the threshold, we do that, we just cut the surface of the real field here to have just 2 phases, because it's easier to design our phononic crystal or metamaterial just with 2 phases. So if you compute the Fourier transform of our material or geometric distribution, we also have the same spectral content of our design with small peaks here because we have some approximations, because we limited the domain, and also because the threshold. But what happens if we put some symmetry that is not allowed for the crystals? Okay, now we fill the space again, but we don't have a unit cell here. We have some order. The space here, some geometries repeats on space in X or Y. We have the rotational symmetry, but we don't have a unit cell definition in this case. Okay, and this is interesting. Let's see what is the wave properties that this kind of geometry has. And also they keep this domain here, this distribution, they keep the Fourier or the spectral contents of our design like before. Okay. But we want to use these distributions or these designs to obtain a real plate or a real material or a real structure. And we did that. These two first steps here are like I showed before. And instead of use two materials, we use just one material with a modulation in the geometry. So we strut like pillars in the black phase here. So we can construct this material in 3D printing. In one of the sides of the plate is flat, and the other we have these pillars here, okay? And we did the same for other fold symmetries, like the 4-fold, 6-fold, and 8-fold. So we can compare the quasi-crystals with the crystals. What is the common, what is different between them, okay? But how we can investigate these quasi-crystals if we don't have like a translational periodicity? So we cannot apply the Bloch-Floquet conditions in the boundaries of these quasi-crystals. How you define a unit cell? So we used an indirect approach based on the time simulation. With this time simulation, we have a full space. We recovered the displacement field in x, I, and time. So we have a full populated cube here with points with displacement, okay? And we can compute the Fourier transform to transform the physical space in reciprocal space. But again, we have all the points here in this cube, it have a wave, so we cannot see anything. So we need to apply a filtering in this Fourier transform. So we neglect the waves with low amplitude because they're not influenced on our dynamic response. And now only consider the waves with high amplitude here. So we can see the spectral contents that you wanted. And the advantage of this procedure is that we can compare with the experiments also. So if you perform the experiment on the plate, like you have your excitation in the center and you measure the displacement field for several times, you can do this same procedure and compare with the numerical simulations, okay? So let's see what you have for, but first, we also validate this procedure for the 4-fold. So we can compute the band structure by applying the Bloch-Floquet conditions. And this is our approximated band structure. So we can see that the gaps match in 10 and 50 kilohertz, but also the propagating band are the same. We can see the frequency zones here. But in our case, for the 4-fold, we don't have any anisotropies, so we have circular wave number contours. But what happens for the quasi-crystals? Because we have the same pillars for the crystals, for 4-fold and 6-fold, we have the same pillars. So it opens band gaps in the same frequencies here for the 4-fold and 6-fold, okay? And our propagating band, it's isotropic. But for the quasi-crystals, we also have the gaps here around 10 kilohertz and 50 kilohertz, but this band here splits in several bands. So we have a fractal nature of these bands because the fractal nature of the quasi-crystals. And they are highly anisotropic and they change with the frequency. So we can use these bands to manipulate the waves in a better way and also to have a high order wave beaming, as we'll show in the next slide. So these are the dispersion properties that we also, for the case of the 10-fold case, we also validated with the experiments. So we can show here that the bands, the dispersion contents, they are rotated. If we change the frequency, we have it like a twist. And the transition band, it's like a circular contour with almost isotropic behavior. for both the simulations and the experiments here, you can show like good results that they match. Okay, but let's see what happens in the time domain, in the physical domain. If we consider a frequency here almost closer to the first gap, you can see this beaming in the tenfold symmetry. If you change the frequency to higher frequency, you can see that the beaming happens twisted between this one. So these results expand the results of the crystals, because before the beaming was just allowed in the symmetries of the crystals, like 4-fold, 6-fold, but not in 10-fold. So we can show that these results can use in a better way. So we can create beaming in other fold symmetries, in the fold symmetries that you wanted, in 8-fold, 10-fold, or 12-fold symmetries. Okay, and we also compare these results with the experiment, and they match very well. This is the time, we increase the time. These are the snapshot, and these are the Fourier, the spectral content. They are also the same, and we can see the beaming also in the experiment. Okay, and now I will also show some diffraction results. But for this case, we have half of the quasicrystal, and around this quasicrystal, we have a uniform plate. So let's see what happens here. We have this quasicrystal, just a half, so the middle of the quasicrystal is here. We have an incident wave here with a certain thickness, okay? And when this incident wave here reaches the quasicrystal, they will excite all the Fourier points on the quasicrystal. So the wave here will branch in the fold symmetry that we saw in the beaming before. When we rotate the quasicrystal, the same happens. So the incident wave will excite all the Fourier points of the quasicrystal, because the thickness of the incident wave is small, so we excite a large band or a broad band in Fourier domain or reciprocal space. But let's see what happens if we increase a little bit the thickness of the incident wave. So we will excite only 2 points in the reciprocal space, so we can focalize the wave in one direction, or we can branch in two fronts here like this, so we can manipulate the wave front the way that you wanted with 1, 2, 3, or 4 brains, okay, using quasicrystals that is not possible to do also with crystals. So these are the results that I would like to show. I don't know if I took so much time to explain, but these are the conclusions that the wave directionality and diffraction along the higher order symmetric directions, and also we expanded the wave behavior beyond the periodic configurations. Okay, and we published already this paper in the left that I didn't show the results, but it explains a lot of the designs, and the results that I showed today we'll publish soon. Maybe it will be on archive soon. So thank you.
Thanks, Danilo. Thanks for your talk. Showing again our schedule. So I'd like to invite Jaime Alberto Mosquera Sánchez to talk about nonlinear piezoelectric metamaterials. So Jaime, when you can share your screen, start when you are ready.
Okay, so can you hear me?
Yes.
Let me show my slides. Okay, so can you see my slides right now?
Yes, Jaime.
Yes.
Okay, so hello everyone. My name is Jaime, and And this is my postdoctoral project, which is entitled Control and Energy Harvesting for Low Frequency Vibroacoustic Disturbances with Smart Metastructure. And today I will show you some recent results from this postdoctoral project, which has been sorted according to the way in which I approached my project. I will show you some lumped parameter results. After that, I will show you some results we collected in a 1D beam. So in a 1D metastructure. And after that, I will show you some preliminary results on the effect or mono resonators, monostable resonators, and bistable resonators. So basically speaking, my configuration, my metastructure configuration, consists of a mechanical host oscillator, which is piezoelectrically coupled with a nonlinear circuit. And this circuit features a negative capacitance, which is intended to compensate for the linear effects that are imposed by the inherent piezoelectric capacitance. And also, we're including a cubic electrical element to give the nonlinearity to the circuit. So in this case, we are attempting to study two sorts of oscillator. The first one is the Daphne oscillator, which is characterized by a large linear term, and the second one, which is characterized by a essentially nonlinear force, which is given by this component. So in a first glance, we started by studying the lumped parameter models, and we started studying the effect of the cubic part in the dynamics of the system. And we unveiled some effects, some nonlinear effects, which are given by the cubic part, in which as the level of nonlinearity increases in the system, we see that the jump phenomenon happens at both the in-phase nonlinear normal mode and the out-of-phase nonlinear normal mode. In the right side, we have the effects of the nonlinear part in the essentially nonlinear oscillator, in which, for this case, we only see a small effect in which the in-phase and the out-of-phase modes are starting to depart from each other, attempting to give a broader effect in the dynamics of the system. Well, and after that, we departed to integrate the equation of motions for a set of 20 nonlinear unit cells, and we verified the effects of the nonlinear part and the negative capacitance part. Well, so in order to understand the effects, we also developed some analytical expressions to study the band structure of such a unit cell, in which we identified that as the level of nonlinearity increases in our system, the band gap limits and the location of the band gap and the limits start shifting to the right side, to high frequencies. And we also verified such a behavior with the forced responses of the system, in which we can also see that the band gap limits or edges are starting to shift to the right side. And another particular observation we also obtained is that as the level of nonlinearity increases in the system, the band gap starts becoming dominated by some harmonic and quasi-periodic solutions, which are approved of the wave supertransmission effect. Such an effect can be traced back to the emergence, of the fault bifurcation, which is happening, let me show, at the first in-phase mode. So as the fault bifurcation starts shifting to the right side, the wave supertransmission effect becomes apparent in the responses. And this effect is happens at both kinds of oscillators. I mean, in the Duffing oscillator and in the essentially nonlinear oscillator as well. Well, moving to a distributed parameters model, we used a 1D beam provided with several equally positioned unit cells with the same parameters, and we started studying the force responses of the unit cell, in which we found the same effects as the ones we found in the lumped parameter models. And we also could study the transmissibilities of such kind of unit cell, in which we can see that as the level of nonlinearity increases in the system, the transmissibility in this case becomes flat within the band in which the transmissibility is low. Those results are related to the unit cell. So in order to study the metastructure effects, we integrated the equation of motion for a set of 12 unit cells in a beam. And I will show you only the transmissibility results, in which we can see the following observations. So along the rows, we can find the effects of the negative capacitance, in which we can see that the band gap, the linear band gap, is opening as the negative capacitance improves. And we can also see the effect of the cubic part in the circuit, in which we can see that as the level of nonlinearity increases in the system, the band gap's limits becomes shifted to the right side. And as the level of the nonlinearity becomes quite high, we can see that the transmissibility gets flat, as and this is due to the effect of the wave supertransmission effects. In the columns, we can see the effects of the damping in the electrical circuit, in which we can see that for the for the Duffing oscillator, we can see that the small band gap starts becoming apparent. And as the damping becomes more evident in the system, the damping becomes the dominant mechanism in the system. So the cubic part becomes masked in some sense, giving rise to more linear effects. And such behavior was verified in the other combinations of the negative capacitance. Okay, so those are the results from my metastructure. And last, I will show you some preliminary results on the effect of monostable and bistable circuits in the system. This slide is quite heavy, so I will ask you for wait a while. Okay, so and those results are based on the sign of the negative capacitance, in which, as we have a linear positive residual capacitance in our system, we will have monostable resonators. While if we have a linear but negative part in our oscillator, we will have a bistable resonator. In those cases, we can see that we can shift the edges of the of the band gap of the band region in which we have a transmissibility below 1 to the right in the monostable case, while for the bistable resonator we can move the band gap edges to the other direction, I mean to the left direction. For this case, I have some troubles with this slide. I will show you my other presentation that I prepared, but in Portuguese, and only to show you the time domain behavior in which the interwell and intrawell displacements are quite evident. Oh my God. Can I write or not? Okay. Oh. So for the monostable case, we have the displacements around one stable point in the 0, point. And for the bistable case, we can see, okay, the intrawell and interwell behavior, which effect accounts to shift the band gap limits to the left side instead of the monostable resonator, which shifts the band gap limits to the right side. Okay, so, oh my God. No, I will be unable to show you the responses. Okay, so as for the lowest nonlinear regimes, we can see that the displacement happens around one stable point, which is offset from the 0 position. And as the level of nonlinearity increases in the system, we can see some intrawell and interwell displacements, while the highest nonlinear levels will show quite quasi-periodic and chaotic behaviors. So those are preliminary results which are still under study. So let me conclude with some ongoing work. But yeah, my computer is about to crash. Okay, so to conclude, I will show you some numerical works which are ongoing. So the mono and bistable resonators are currently being integrated by using some high-performance computers here at the University of São Paulo. We're also approaching some plates to see the effects of the negative capacitance and the cubic part in the vibration attenuation. And finally, we are also studying the band gap formation using internal resonances. So this is my presentation, and thank you very much for your attention.
Thanks, Jaime. So thanks for your presentation. I would like to invite Renan Lima Thomes, our fourth speaker today, and his talk is Space-Time Wave Localization in Piezoelectric Metamaterials. So Renan, you can start when you are ready.
Let me share my screen. Can you hear me?
Yes.
Okay. Can you all see my screen?
Yes.
Okay. Good morning, everyone. My name is Renan, and I'm going to present this project that I was working on with Danilo and Professor De Marqui. And it's called Space-Time Wave Localization in Metamaterials with Programmable Defects. Here's a brief summary of this presentation. At first, I will give you a quick introduction on defects and piezoelectric materials. Then I will present our electromechanical system that we are studying. And for that system, I will show you the results for fixed and then for programmable defects. And I will end this presentation with some concluding remarks. So we all know that a series of local resonators attached to a host structure will open a band gap close to their resonance. And if we have a defect in one of those resonators, for example, a different mass here, that will cause a defect band to appear inside that band gap and wave localization around this defected unit cell. However, can we somehow replace those defects along the structure in order to concentrate energy at specific locations and specific times? Well, with piezoelectric materials, we actually can. So for those who are not very familiar with this, a piezoelectric material connected to an inductive circuit composes our local resonator, where the inherent capacitance of the piezoelectric element is equivalent to the spring in mechanical absorbers, and the inductor is equivalent to the mass, such that the resonant frequency of this resonator is given by this formula, and the C norm here is just a constant to normalize the frequency. But the point here is that we can actually change these inductances with respect to time by using digital circuits or even analog circuits too. So with this, we can modify the properties, the dynamic properties of these resonators as a function of space and time. And for doing this, we are studying this electromechanical metastructure. It is a beam composed of 21 local resonators and unit cells. And throughout this presentation, I will say that a resonator is in the periodic configuration if its resonant frequency equals omega t, which is the tuning frequency. And I will say that the resonator is in a defect configuration if omega n equals 2 omega t. And the band structures that I showed you before are actually for our electromechanical supercell. So when all the resonators are in the periodic configuration, we have the traditional band gap here. But when we have a defect at the 11th resonator, which is in the middle of this beam, we'll also have this defect band with concentrated energy around here. So after this spectral analysis, we're going to study now the time domain response for a fixed defect. And for this, we're considering free boundary conditions. And we have also a defect at the 11th resonator here. And we are applying a point load in the middle of this beam, which is a sine burst at the defect band frequency. And for these considerations, we have this response. Actually, this is the envelope of the response. But here in the left, we have the transverse displacement of the beam as a function of time and the position along the beam. And as expected, we have concentrated vibrations here around the defected unit cell. And this figure here in the right shows the voltage output in the piezoelectric elements. And notice that for the resonator that has the defect, the voltage output is almost zero since it's excited far from resonance, and maximum voltage occurs in the cells adjacent to the defect. Now we are going to program those defects along the structure. That is, we're going to replace those defects along this beam. And for this, we're going to impose a law to the resonant frequency of those resonators. But remember that we are actually changing the inductances of these circuits. So this is how it works. For the JF resonator here, I can change from a defect configuration when omega n equals 2 omega t to a periodic configuration when omega n equals omega t. And for this, I use this equation here in the middle, which is a simple cosine function. Or I can also do the opposite, change from periodic configuration to defect configuration using this equation in the bottom. But the idea here is to do both things simultaneously for successive cells. So while I'm removing a defect from the JF resonator, I'm also adding another defect to the J+1. So for example, if I'd like to control the defect from the 11th resonator to the 20th one, I would modulate the electrical resonances like this, gradually tuning and detuning neighboring unit cells until the defect is left at the resonator number 20. Moving now to the actual results for these programmable defects. We are considering the same beam as before with the same point load here, but this time we will begin with a defect at the 11th resonator, and we will reprogram it to the resonator number 12 and then to the number 13. And for this, we are using this modulation of resonances here. And the results for this system are here in the right-hand side. Here in stage 1, we have the same behavior as before. We have concentrated vibrations around the 11th resonator since it has the defect. But then in stage 2, notice that the energy is gradually transferred and split between unit cells number 11 and 12, since both of those resonators are not in the periodic configuration. Then in stage 3, the energy becomes again localized around a single unit cell, but this time the number 12, since it holds the defect. And then for stages 4 and 5, this process repeats, and we end with localized energy around the 13th unit cell, which was the purpose of this modulation here. Also notice that the voltage output has a similar behavior as I showed you before. For the resonators that are not in the periodic configuration, the voltage is almost zero, and maximum voltage occurs for the resonators adjacent to the defects. So the point here is that we can use the same strategy to localize and transfer energy to any point along this structure. We just have to play with this modulation here. Moreover, we can also apply these concepts to more complex systems. For example, by combining 3 of those beams, we can make this triangular lattice here. and localize energy in space and time as well, and by using the same strategy. Or we could also build other repeating units and make other structures from those units. In conclusion, we presented a piezoelectric metamaterial whose space-time modulation of the resonant shunts creates programmable defects, and our strategy perfectly transfers energy between subsequent unit cells and confines vibration energy in space and time. And these concepts may also be applied to guiding, sensing, monitoring, and energy harvesting. With this, I conclude my presentation. Thank you for your attention. If you have some questions, I'd be glad to answer them. So before I stop talking, or while you think, I'd like to show you a video of the theme that I presented. So we begin with localized energy here at the middle, and then as we change the electrical resonances of the system, this energy begins to be displaced and transferred to the right-hand side of the beam. So if you have some questions, I can answer them now. Thank you.
So thank you, Renan. We will open for questions after the last presentation, okay?
Okay.
So thank you for your talk. So I would like to invite Camila Sanchez Schmidt to share her slides and start her talk on piezoelectric energy harvesting from disordered structures.
Good morning.
Good morning, Camila.
Can you see my screen?
Yes.
Yes. Mm-hmm.
Good morning. My name is Camila Schmidt. I am a master's degree student, and today I present some results of the project that Professor Wagner, Professor De Marqui, and I are developing, entitled by Piezoelectric Energy Harvesting from Disordered Metastructures. The work will follow these contents: the introduction. In the theoretical background, the governing equations of a cantilever biomorph beam will be summarized considering model analysis. In the results, the graded elastic metal structures will be presented, the effect of variability in the band gap formation, and the piezoelectric energy harvesting will be analyzed in two cases, for continuous and segmented configuration for the electrodes. Finally, we will draw some remarks on conclusions. The band gap is a phenomenon where the propagation of elastic or acoustic waves are forbidden, which can be obtained in phononic crystal due to Berg scattering, or in locally resonant metamaterial, where one important feature is the ability to form low-frequency band gaps. Since the discovery of these metamaterials, many researchers have investigated how to manipulate waves using them. While many studies have considered identical resonant elements, a new class of metamaterial have attracted the attention of the researchers, known as graded metamaterial, which can be obtained from a variation in some parameters of the local resonators. And this variation produces band gap widening, wave trapping, and energy localization. And this energy localization can be used to enhance the energy harvesting capability. However, the energy cancellation occurs when continuous electrodes cover the strain nodes. Then, in present work, a criterion for electrode segmentation will be presented to avoid the energy cancellation. The system studied is a cantilever bimorph beam made from aluminum substructure with piezoelectric ceramic layers of PZT5A under harmonic base excitation with 15 mechanical absorbers. The configuration for the electrodes for energy harvesting will be analyzed in two cases, for continuous and segmented one. But in all cases, they are connected in parallel by a resistive admittance. The governing equations for the bimorph absorbers and shunt circuits were obtained considering Euler-Bernoulli theories. Then, assuming Harlequin's expansion, we can obtain our equations in model domain for the bimorph, absorbers, and shunt circuits. Then, assuming that the response of the system is harmonic at a target frequency, we have the amplitude for the absorbers and voltage amplitude. And substituting this expression in model governing equation, we have our final expression. To obtain the graded metamaterial, a variability in the frequency of the absorbers, which follows this linear law, was adopted, where omega k is the natural frequency of the beam, beta is the slope disorder degree, n is the number of absorbers, delta is the distance between them, and L is the length of the beam. From the figure, it's possible to see that as the disorder increases, the bandwidth increases. And high disorder produces peaks of vibration between the individual band gaps. And positive beta values exhibit fewer band gaps than negative one. The transmissibility was investigated for descending, uniform, and ascending pattern. For the descending and ascending pattern, it's possible to see that the bandwidth varies along the frequency and metastructure length. Then the wave trapping phenomenon occurs below a reflection interface that divides a propagation and non-propagation zones. And when all the absorbers are tuned at the same frequency, a uniform and well-defined band gap is created. As already commented, as the variability increases, the bandwidth increases. But if we consider high disorders, peaks of vibration are created between the individual band gaps. And to investigate in more details the effects of variability in the band gap formation, the tip transmissibility was plotted for different beta values, where the blue line corresponds to the uniform case, the red line corresponds to the ascending pattern, and the orange line corresponds to the descending pattern. And to make this comparison, an approach presented by Celerol and Al-Shakak was adopted, where we consider that we have a band gap when the tip transmissibility is equal or minor than O.1. From the figures, it's possible to see that the uniform case presented the highest intensity attenuation, different from the descending pattern that presents the smallest one. And for this pattern, if a high disorder is adopted, peaks of vibration are created between the individual band gaps. But for the ascending pattern, as the variability increases, the bandwidth increases too. And for these cases here, the peaks of vibration aren't created. The transmissibility versus dimensionless beam for the uniform case, and when a beta equal to O.421 was compared. From the figures, it's possible to see that for the uniform case, the energy propagates along the entire substructure, different from the second one, that the energy propagates until 70%. And this phenomenon can be used for energy harvesting. Then, considering this frequency and this disorder, the energy harvesting was analyzed for a continuous configuration for the electrodes. And the maximum power harvested is when a resistive load equal to 500 ohms is adopted. But as presented by Ertuk et al., vibration of modes have certain strain nodes where the dynamic strain distributions change sign. Then covering these strain nodes with continuous electrodes, cancellation occurs. To explain more details, the effect of strain nodes, the electrode segmentations, let's recall the shunt circuits again. From the equation, it's possible to see that the excitation is proportional to the integral of the dynamic strength distribution. Or in model domain, it's proportional to the sum of the projected model velocity and model coupling. And the most critical term here is the model coupling, because it's function of the bending slope evaluated at the boundaries of the electrodes. Therefore, if the difference slope is large, the contribution will be large. If the electric charge developed at opposite sides of a strain node is collected by a continuous electrode, cancellations occurs due to the phase difference in the strain distribution. Mathematically, the partial areas over the integrand term will cancel each other. Then, to avoid the energy cancellation, the curvature was plotted, and 8 segmented are necessary for this frequency and this disorder. Then, the power output was again analyzed for this configuration. Here are presented the figures that have the highest powers, that are the second, third, fourth, and fifth segments. When you compare the total power of the 8 segments with the continuous configuration, it's possible to see that strong cancellations occurs. The curvature was plotted for frequencies where the energy localization occurs. And it's possible to see that for each frequency, a new pattern of segmentation is necessary. And for these frequencies was again compared for continuous and segmented configuration. And in all cases, a strong cancellation occurs if we adopt a continuous configuration instead of a segmented one. From the results previously presented, it's possible to see that the variability increases the attenuation bandwidth, and the wave trap and the energy localization occurs, and this phenomenon can be used for energy harvesting. Then, when you compare a continuous configuration with segmented one, a strong cancellation occurs if you adopt a continuous configuration. Thanks for your attention. Does anybody have questions?
Thanks, Camila. Thanks for your presentation. So now we open for discussions and questions, suggestions for all the presentations.
Should I remain recording or for the questions or notes?
I think so. So Paulo Palpites raised his hands. Paulo, please.
Hi, Carlos. Yeah, well, thank you very much for the presentation, guys. It was nice to see what you are doing. So I was going to ask many questions, but maybe I'll try to ask Renan first and let the others go around. Renan, I saw your work, and it's very interesting. I was curious about your simulation results, where you were tuning the frequency for the resonator, right? In that simulation that you showed, where you have the animation, do you have a fixed frequency, or was it a burst excitation? I didn't get that.
Yeah, it was a sine burst excitation. So in the beginning, we have an sine burst, and then there is no excitation at all.
So, and what's your intention with the localization? Do you intend to provoke some energy harvesting capability or something like that? Is that your?
Yes, we are still very in the beginning of this idea, but I think we could use it to energy harvesting and also monitoring and perhaps guiding in two-dimensional structures too.
Okay. Okay, thank you, Renan. Really nice. Thank you.
Thank you.
Paulo, if I can complete, at this stage, what he's showing that after this excitation, he can manipulate the energy to any point of the beam or of the lattice by programming these defects.
Okay.
At this stage, actually.
Okay, yeah.
So thank you.
Thank you.
I think, let me see. I can see everyone. Vinicius Cleant raised the hand. Please, Vinicius.
Hi, everyone. I'd like to thank for the presentations. I have a question for Leopoldo, if it's okay. You have shown a color map graph about the transmissibility, which is a function of the frequency and the number of cells. I don't know if I am wrong. You have shown there the band gap formation.
Yeah.
As a function of the frequency and the number of cells. Can you explain why with a small number of cells we get a relatively small bandwidth, and when we increase for a certain, yes, exactly, this one. For example, you increase for a certain number of cells, this bandwidth increase considerably.
So, yeah, so first of all, so the white lines here are the resonances. So when these membranes will resonate, they will transmit a lot of noise. And in between, we have the anti-resonance plus the shunt damping. When we have one of them, it's quite concentrated. We have that notch in the frequency response function. When we increase the number of unit cells, yeah, there's a mix of things there. We cannot claim we have Bragg scattering because it's the super wavelength, but it's a way of introducing a distributed dynamic absorber. Let's see. Some people refer to phonotype metamaterials because then this phenotype is related to some solid state physics where you have resonances again.
But there is any particular reason, for example, it looks like after 5 number of cells, these attenuation bands increase dramatically. Yeah.
Maybe it's the color scheme here, but it's I don't know.
It's there. Okay.
I would expect it's more. It's not that abrupt change.
Okay.
Maybe it's just the choose of color, but I don't know. Maybe you're right. That after here you suddenly. Sorry.
No, okay. I get it. I was misinterpreting this graph too. You have this attenuation band since from the unit cell, all right?
Yeah, right. So here.
Okay, that's it, my question. Thank you.
Thank you, Vinicius. Arruda, please.
Yes, so good morning, everyone. Thank you for the presentations, very interesting work. I was going to ask another question, but I'll start with the last question asked to Leopoldo. In this case, you have when you have the transmission loss case, you're talking about cells, but I don't see the periodicity would be in plane. I don't get exactly what's your periodicity. When you increase the number of cells, actually you're increasing the number of obstacles to sound. So is there any property related to this periodicity, or it's just the fact that you are adding up the transmission losses of each layer of your cell? And also I'd like to ask, how do you compare the transmission loss with the same structure, but without the shunt circuit. So that's just a passive obstacle to sound.
Yeah, so maybe these plots will help us better than the previous one. So first thing is, indeed, we had, it's a plane wave exercise, so the wave is hitting those membranes like directly facing forward. So if we would have then a full panel of those membranes, the behavior would be basically the same, right? So when we do the waveguide, either numerically or experimentally, we are trying to simulate just these plane wave incidents on the panel. And by adding several layers, then it's a bit the same as I imagine it. If you have a rod, like in a crystal, and you start adding resonators to your unit cells. So in a way, you have that. You also have the transmission loss phenomenon, but you are adding layers, so you have more mass in your system. And to try to avoid that interpretation there, we add a penalty sometimes to these analyses. And this penalty is we decrease 6 dB from the transmission loss every time we double the mass of the system. So when I start with one cell, I have certain transmission loss. When I put the second layer, we analyze the transmission loss, but then we remove 6 dB from there to say, okay, that's 6 dB from the doubling of the mass, if we are close to Mass law anyway. And we were doing it as such. So every time we added a new layer, we analyze it again and penalize the curves. That's in one side. On the other hand, there's also this thing that we did not try yet. That was just removing the membranes from here and leaving out the frames to see what's the effect only of the shrinking and like you already have a filter there, right? An acoustic filter by changing the cross section. Pedro, who's my master thesis student now, is also trying to simulate that without the frame. So an ideal case where we don't occupy any space with the framing, to see only the membrane behavior, how does it go, and then after that adding a frame and really like splitting the contributions of each element to the phenomenon.
Okay, thank you. Yeah, now I understand what you were mentioning, what you meant by the penalty. Okay. Yes, it would be interesting to try to have a waveguide formulation, analytical or numerical. Analytical, I think, even if it's approximate, to try to come up with a let's say dispersion diagram for the system and look into the physics of this, which is not usual. So I understand the periodicity is, if you use that along a waveguide, a tube, that's the basic idea. And then there's another periodicity, which is the plate 2D periodicity, which would also play somehow.
Yeah, and the third thing I would add is that there we try to explore an anti-resonance effect. So if we take only the passive membrane, I stopped sharing my screen, sorry. If we take only the passive one, so we have the resonance, the internal resonance of the unit cell is something we want to avoid actually, because that's where the noise will be transmitted. So we're trying to explore the anti-resonance there. And what happens when we add those systems in a periodic fashion with anti-resonances? It's not really a resonance.
And they may couple, of course. They can be coupled through acoustics. Yeah. Thank you. Interesting. Thank you, Leopoldo. If I may, Carlos, just a question which will be sort of a general question for discussion, maybe at the end. Just let people ask particular questions, and then we could make a discussion, because there are two approaches. Renan has shown how to program defect and make it, put the defect wherever you want in a periodic medium. And Camila showed how to use varying properties to trap energy for energy harvesting. So you can try to increase or concentrate the energy for energy harvesting purposes using varying properties, using defect, using topological modes. It would be interesting to somehow compare those, what is best? And also a question that I ask you as a specialist of energy harvesting. When I work, the student of mine, Lucas, has worked with topological modes for energy harvesting, but the problem is you get concentration of energy at high frequencies. It's hard to make it in very low frequencies. And usually piezoelectric energy harvesting is done at very low frequencies in a resonating system such as just a simple beam, for instance, cantilever beam. So what is feasible and what is best if you think about energy harvesting by manipulating waves?
Yes, I don't know how to answer this question, to be frank, but what we did in Camila's case is harvesting from localized mode. That's all. The piezos are there only for harvesting, not for any resonance. And I'm not sure if it was clear what she showed is how to segment electrodes to improve or to enhance this harvesting from these localized modes. And a lot of energy or electrical output is cancelled with continuous electrodes. But I understand that we can think in energy harvesting from different wave phenomena. You're right, but to be frank, I don't know. I can't answer which one is the best one. Maybe it would be interesting to explore them and compare in the future. But,
yeah, given that you have an experimental setup that might allow to try different approaches.
Yeah, but even in her case, it's not very simple because we have many different localized modes, and for each mode, we have a different optimum pattern of electrode segmentation. So it's like it's very frequency oriented. So in practice, it's not something simple to have a very flexible configuration of piezo segmentation to be optimized for different localized modes. For sure.
Okay. Thank you, Carlos. Thank you, Leopoldo.
Thank you. José Maria, please.
My question is related with the same that Arruda commented in Leopoldo work. I have been seeing this. I understand that your membrane works like a local resonator. It's close what I have been working, like if you using a duct, some local resonator, then what I have been seeing is not like a penalty, but people used to do an average.
Yeah.
You know, if you calculate the TL for one resonator, you divide by 1, but if you have like 2, 3, 4, you divide by the number of resonators that you, and seeing that the result works fine also. It's merely a comment, it's not a question. Okay.
Yeah. Thanks. Don't see any more raised hands. Do you, Carlos?
Any other question?
Maybe while people think about the next questions, I'd like to ask Danilo, in the beaming, very interesting properties of beaming of quasi-crystals, we don't see a very sharp beam being created. It looks like it's quite attenuated, so you see sort of a tendency to propagate in given directions, but it dampens very quickly. Can you comment on that? Can you improve this behavior of having a more far-reaching beam?
Yes. Maybe.
Or maybe I was thinking maybe because of 2D FFT and 3D FFT, you need some damping to improve the behavior of the transforms or something.
No. I think that I understand your question, because you are thinking about this behavior here, about the frequency. But if you check the first frequency, they goes far.
Okay.
Because this here, it's just 20 centimeters, the domain, the plate, the side.
Oh,
but
this is the size of the whole plate.
Yeah, this is the size of the whole plate. But for diffraction, if you check here, we increase the domain in this side, just a half here of the quasi-crystal, but we increase in this direction. But the wave goes far, the directivity or the focalization goes far. So depends on the time simulation too. If you put a lot of time simulation, because this one's time simulation, it's not frequency. So depends on your vector, time vector.
Are you using finite elements there?
Yes.
So it becomes very huge, large problem if you increase the size of the plate.
Yeah. You take some hours to compute. And also depends on the time vector.
So, but this is not a limitation of the property, it's just a limitation of how to simulate it.
Yes. And for plates like these, we don't want to reach the border, because if you reach the border, you will see some reflection, so it will be hard to see the beaming phenomenon too.
And I suppose there's a lot of there are many signal processing issues in using this method of based on Fourier transforms.
Yeah,
I was wondering if you could improve it with wavelets, for instance. Or...
Yeah, could be. I don't know. I didn't try with the wavelet, but yeah, can improve the method with this other processing. But it's slow. It's a lot of data, and to compute the Fourier transform, like I did here, I use small parts and of the time simulation to reconstruct it. But I need also to improve here to become more smooth, the transition between one simulation to another. But yeah, it's a lot of time to compute this.
Can I take advantage of... sorry.
Go ahead.
Thanks, Arruda. So, Leopoldo, please.
Yeah, just take advantage of the slides that are shown. Danilo, from a practical point of view, I assume you built those plates with selective laser sintering on ABS or something like that?
Sorry? Leopoldo?
They look like plastic, they look like polymer, it's like selective laser sintering.
Yes. Yeah, it's the normal one.
And then you measure it on the flat side of the plate, right?
Yes. We measure in the flat side and also exciting the flat side of the plate.
Okay, and the equipment you use, because it's a white plate, do you need any treatment on the surface?
No. This is scanning laser Doppler vibrometer. We don't need any treatment on the surface. It's just a measure. But you can also put some reflection material to improve the measurement, but it's not necessary in this case.
And it's measuring in plane vibration.
Out of plane vibration.
Out of plane.
Yes, because this laser, it's just measure one axis, so we are measuring just the out of plane, so the flexural or band waves that you are interested in.
You need a very fine mesh. You need to measure on a lot of points to come up with those plots.
Yes.
How long does it take? How long does it take to do a full measurement of the plate?
I didn't perform the experiments, was Mateus. I just processing the data, but I think that it takes a half hour maybe, or 15 minutes. It's not too long.
And if I may add, you measure the flat surface.
Yes, the complete flat surface.
So thank you. Any other question? Breno, please.
Hi, yes, hello. Thank you for the presentations. I really enjoy this subject. I have a question which is sort of in line of what Professor Arruda asked before. Because generally from what I understand, piezoelectric harvesting is performed from low-level vibrations, right? So if you add periodicity, Bragg scattering, and localized energy phenomena, you generally have higher frequency. You analyze higher frequency vibrations generally. Now, what I would like to know is if you take into account, or rather compare, energy harvested from these higher frequencies, such as Camila's electrode segmentation strategy, to first order frequency vibration energy harvesting, like a simple cantilevered beam with continuous electrodes. Like, do you compare the possible harvested energy from these, or it would be interesting.
Okay, thank you. No, we have not compared. But you're right. I'm considering here if.
On the other hand, you could argue that for many ambient vibration sources, you don't have very low or that low vibration, and you're just studying different methods to increase the.
Yes, it's a very theoretical case in her work, but I think we can bring this localized modes to lower frequencies and do energy harvesting. I think Camila is targeting the third mode of the beam, isn't it, Camila?
Yes.
So it's the third bending mode of the beam. So it's not very high frequency. It's really below the first Bragg group.
Okay, I understood differently because of the. I think it was. Yeah. Okay. Thank you.
Okay, thank you.
Just if I can add some comments on that.
Yeah,
you said about Bragg scattering. We are actually using like local resonators, so it doesn't require really high frequencies. For example, in my case, we were in 1,000 hertz, so it's not that high,
And since you've commented on this, I have another question for you, Renan, too.
Okay.
Does your strategy of, like, from what I understood, energy propagation, controlled energy propagation, do you require also external current to?
No. We just change the properties of the circuits, but it doesn't require any voltage source or currents. But it does, if you're using digital circuits, you do need a voltage source to power the digital components, but it's not a big thing.
Okay, thank you very much. That's all.
So he's using the direct piezo effect. So I was thinking about your first question for Camila's work. I'm not sure if it was clear. The resonators are spring mass systems, so it's an elastic metamaterial, and the piezos are there only for harvesting. That's the point. So it's a resonant metamaterial. So it's a resonant effect. It's not Bragg.
Oh yes, I mentioned Bragg, but I meant it as like both in general, like for phenomena.
Okay.
Yeah, no.
Thanks. But I believe her case it's low frequency.
Localized resonances and low frequency.
Yes, and maybe one advantage for, let's say, a plane beam, it's for energy harvesting, you have separated resonances. In this graded metamaterial, you have many resonances or peaks very close to each other. So maybe we can take advantage of this very high number of peaks in a relatively narrow frequency band for energy harvesting.
Though, in general, and here I might be wrong.
Mm-hmm.
I'd like you to tell me. Aren't these the possible amplitudes of these voltages in periodic materials generally lower than from a single beam, for example? Or no, it doesn't matter as long as there is resonance.
Depending on the amplitude, and specifically for this case that we have many strain nodes along the length, if you have continuous electrodes, the net voltage output will be very low because there's a lot of cancellation.
Yeah.
That's what she's showing, that you can avoid this cancellation and improve the harvested energy in case you're interested in energy harvesting from localized modes.
Okay, thank you.
You're welcome. Any other question? So, thank you all for attending. Available in our websites, and we will contact you to invite for the next seminar that should be next month.